right, our topic for today is titration. So what we're trying to do is we're trying to figure out, okay, so what do I do this thing for? It's kind of a famous, in the chemistry world, like a famous procedure known for, well, what? What's it for? Well, the purpose of a titration is to take the addition of you start with a solution that you know how much you're using it. So a known amount of solution. So you know how much you're adding to determine the concentration of another solution. So you've taken data, you've measured how much you added, you know how much you started with, and then you can do some calculation to figure out the concentration. Okay, that's the general idea, but what's it used for? Well, let me give you a visual here. So it's used for things such as if you are trying to test different solutions. That's usually what it's used for. So it could be medical tests, things like testing human samples of blood or urine to figure out, does it have the right concentration of the chemicals that are supposed to be in there, or does it have an unknown chemical that it shouldn't have, whether it's a drug or a disease or something. It could be used for testing ponds and rivers for pollution things. Again, is there an unknown chemical that shouldn't be in there and there's too much of it and that's causing problems? It could also be used in food chemistry. I worked at General Mills for a while, and one of the things we needed to do is we needed to do titrations of fruit snacks. So we would smash up a bunch of fruit snacks and mix them with some chemicals so that they were like a solution, and then we would do a titration to see the level of acid in those fruit snacks. Because if there wasn't enough acid, it wouldn't taste very good, it would be really boring. If there's way too much acid, it would be way too sour, and then parents probably wouldn't buy those fruit snacks. But other food chemistry can be used for that too. So those are some examples for where I might use an actual titration. So what are they used for? Well, they're used for medical tests. They are used for environmental tests. Environmental tests, and then also for food chemistry stuff. With those examples that I just talked about, but that can hopefully be a reference for you. All right, so that's what we use them for. You are going to be using them in a very specialized lab setting, but you could imagine where this might be used. You could do the same procedure for things like this: medical testing, environmental testing, and then maybe even like food chemistry stuff. So what are the steps? Well, basically what you do is, here's a setup of it. You have this thing called a burette, funnel in it, you've got a flask underneath here, there's a stopper you can turn. That's kind of the setup. You'll have one set up like this for acid and another one set up for base. So what you're going to do is you're going to take a measured amount of an unknown solution. So this is the thing you're trying to figure out about. This could be your blood sample or your pond sample or your fruit snack solution that you made. So this is the unknown solution, and you're going to put that in an Erlenmeyer flask. Erlenmeyer flasks are kind of these triangle shaped ones. And why do you think that's a good shape for something like this if we're going to be adding solution to it and we want everything to stay in? Well, take a look at the shape. The dispenser can go right in there, and when it splashes, it's not going to splash out. If it was an open beaker, those drops could kind of splash all over. So why an Erlenmeyer flask? Because it prevents splashing. And really, more importantly, it prevents splashing out. So you're not losing things splashing out of your solution. Okay, so that's step one. You take your unknown solution, you know how much you took of that unknown solution, like maybe 20 milliliters. It's in your Erlenmeyer flask. What you're going to do next is you're going to add something called an indicator. Now, the purpose of the indicator is to tell you when to stop titrating, because that's when your balanced equation is true, and then you're able to do your calculations. So you're going to add an indicator. The indicator we use is something that's going to go from clear to lightish pink or too dark of pink, like this, if you pass the stopping point, but that's what we're going to use. Then you're going to use a standard, or you're going to use your burette, which is this really, it's like a long, skinny, graduated cylinder that has a dispenser on the bottom. So you're going to use your burette to add a measured amount of your standard solution. The standard solution is the thing you know the concentration of. In this, you have to know at least one of them, because otherwise you have two unknowns and you're just adding two things together and you won't be able to do any calculations. So now you're going to take your thing you know the concentration of, you're going to add it to your acid. So that's going to keep happening, all right? You're going to keep doing this step where you add your standard solution, add your standard solution, add your standard solution until the end point has been reached. And you will know that for our labs because you're going for the lightest color change of that indicator that you added. So the color change of your indicator tells you when you're at your endpoint, and you want to go for the first sign of color change that stays there. That's it. That's a titration. So take the thing you don't know the concentration of, add your indicator, add your standard solution until you get the endpoint, and then that's it. So now you're going to have a bunch of data. But the question is, okay, well, what do I do with that data? So we have our data, now what? The whole purpose of your titration was to get to the moment when your balanced equation is true. Because if the balanced equation is true, we can do our chemistry skills to figure out the concentration of that unknown solution. So let's take a look at what that would be. So let's imagine that you did a titration and this was your data. You took 35 milliliters of your solution, you put that in an Erlenmeyer flask. This happens to be your acid because it starts with H. You neutralize it with 15 milliliters of a 2.0 molarity base solution. We know it's base because of that OH. 15 milliliters, we know the concentration of it, was added to 35 milliliters of our unknown thing. Now let's figure out what we do with that. Well, you're always going to start with a balanced equation. So you're going to start with your acid, H3PO4. Your base, it gives you, was NaOH. This gives us a chance to review neutralization reactions. So because it's a neutralization reaction, acid, base, water, salt, right? Well, the water came from HOH. So I put my HOH in here. And then my salt is whatever's left over. H went away, OH went away, which means I'm left with Na and PO4. Well, Na happens to be +1. PO4 from your peach sheet happens to be -3. So when those come together, I need 3 NAs to balance my PO4. So then that looks like Na3PO4. But now I need to balance my whole thing. Start with your salt always. Says we need 3 NAs, so over on this side I put a 3. Oh, but then now that means there's 3 OHs, and I only have 1 OH here, so I balance that. Oh, now there has to be 3 H's. Oh, there already were 3 H's. PO4, PO4, now it's balanced. Okay. Well, that now it just is what is true now that we're done with our titration. Now let's do our calculations. I'm trying to find concentration of H3PO4. Well, concentration is moles over liter, but of my acid. So I need to know moles of acid and liters of acid. Well, I've got milliliters of acid, so I could plug that in already. But I don't have my moles of acid. So what I need to do is I need to do some stoichiometry to figure out moles of acid. Well, I can't do that until I know my moles of base. So that's where I'm starting. I can use my molarity, so I can use the fact that there's 2.0 moles for every 1 liter of NaOH. I can use that to figure out my moles of NaOH. Well, if I want moles of NaOH, I need to cancel liters. Well, I can do that by starting with my 15 milliliters and turn that into liters. I know that there are 1,000 milliliters for every 1 liter, so that means that 15 milliliters, I just need to move the decimal 3 spots. So really what that means is I've got 0.015 liters of NaOH. So that's a calculation you can do in your head, or set it up dimensional analysis to cancel milliliters and get to liters. So this is really my liters of NaOH. So I can start with that, 0.015 liters. So then what I can do is I can take this math problem, 0.015 liters times 2, and you can do this on your calculator, obviously. I forgot to open mine, so I can do this one in my head. So 0.015 times 0.015 is really 0.03 moles of NaOH. Okay, but remember, I'm trying to find moles of acid. So now is when I can use stoichiometry to switch from 0.03 moles of NaOH, and I can use my switchover step from stoichiometry to cancel moles of NaOH, so that's going to go on the bottom, moles of NaOH, and then I'm going to put moles of my acid, which is H3PO4, on top. I plug in these numbers from my balanced equation. 1 goes with H3PO4, 3 goes with NaOH. So 1 and 3 is my ratio. This is just my switchover step from stoichiometry. Then it's 0.03 times 1 divided by 3. Once again, do that in your calculator, or I can do this one in my head. 0.01 moles of H3PO4, because NaOH now went away, because it's a switchover step. Oh, liters went away up here. So now look, I'm really close. Moles of acid, I just figured that out. Liters of acid, I can figure that out because I know I have 35 milliliters of my acid. Using this same conversion, I just have to move the decimal 3 spots. So that's really 0.035 liters of acid. So now I've got moles of acid, liters of acid. I'm ready to solve my problem, trying to find concentration. So I put 0.01 moles of H3PO4 on the top, divided by my 0.035 liters of my H3PO4 on the bottom. That equals, let me grab my calculator. So now you're just doing a division problem because this is molarity. Concentration means molarity. So 0.01 divided by 0.035 equals 0.286 molarity of H3PO4. Because remember, what I was looking for was concentration. Concentration is molarity. Molarity is moles per liter, but they both have to be of our acid. So remember, making sure that you use the correct thing here. So H3PO4 liters, just like we used the NaOH up here. All right? So those steps will be the same steps that you'll do every time you do a titration calculation. Balanced equation, figure out moles of one thing, switch over to moles of the other chemical that we're talking about, and then divide by liters of that chemical to get your molarity. So that's how you take a titration and actually do some calculations with it. Now I want you to practice that a little bit on your own, of course asking for help as needed. Thanks for listening.